Everyone. Ko tēnā koutou katoa, ko Vivian Aho, no mai, haere mai, ki te Aotearoa Food Safety Science and Research Centre, ka nui te mihi nui kia koutou katoa. My name is Vivian Hunt, and on behalf of the New Zealand Food Safety Science and Research Centre, I'd like to welcome you to our monthly Food Safety Science Spotlight Seminar. And today we're delighted to have Dr. Harry van Inkevoort, who is the Science and Technology Advisor at Assure Quality. Harry has been working at Assure Quality for over 20 years, working across many geographies, sectors, and with regulators, and he leads their process to identify and bring in relevant new science, technology, and digital applications. His science background and knowledge of innovation and technology in the digital space means he's well placed to give us today a futuristic perspective of customer-led solutions for laboratory testing. Harry has a PhD in science from the Waikato University. Following Harry's talk, we're going to have Dr. Tim Harwood, who is the Deputy Leader of the New Zealand Food Safety Science and Research Centre, give us a talk about his work that he's been doing reviewing detection methods, rapid methods of detection of listeria. So Tim is a marine toxin chemist at the Cawthron Institute, and he's co-leader of the Seafood Safety Research Program, which has a focus on developing new food safety tools that benefits industry and regulatory agencies. His research interests include natural toxin accumulation of foods, both in marine and terrestrial environments. And since he joined the Cawthron Institute in 2010, he's worked on many projects investigating natural toxins known to contaminate food. Tim has a BSc and MSc from the University of Canterbury and a PhD from Otago University. He will be joined by Dr. Matt Miller, who's a chemist working for the Cawthron Institute and who has 18 years research experience. Matt leads an international team of researchers that look at the health benefits of New Zealand green shell mussels. He's the president of the Australasian section of the American Oil Chemists Society and the vice chair of the American Health and Nutrition Division at the AOCS. So Harry's going to speak for about 30 minutes, and then we'll allow 10 minutes with Tim and Matt, who are going to show us the website that they've developed as well. So I'll hand over now to Harry, and hopefully you can all mute your as you all have, I think, mute your audios while we're listening, and we'll have questions. You can send me questions via chat. So over to you, Harry.
Oh, thanks, Vivian, and hello, everyone. Thanks for tuning in. And a special thanks to the Centre for the opportunity to present to you all today. Most, if not all of you, will be here because science and tech underpins your business in some way or another. And I've been led to talk today about what I am going to describe to you through my longer horizon view of advances and convergence in science and tech, and also its increasing connection to the digital world, something called hyperconvergence. And it'll be about the things that have become clearer to me when I look back on a lab environment and realise that testing is more about the data and its interpretation than it is about the process, instrument, or test. And also less about IT as a cost centre. So my talk's divided into two parts. I'm going to set the scene first. So if you'll bear with me while I do that. When I look at advances in science and tech and listen to our customer interests, there seem to be four themes. What we can do, where we can do it, when we can do it, and how fast, and what can do it. This is about being sort of in the field or in the processing system and being connected. And these are the four themes that have essentially driven the fourth industrial revolution, Industry 4.0, as it's known, as we have stronger cyber-physical systems. At the same time, there have been a lot of advances in computing and the development of cloud-based systems that have also allowed much broader sort of connectivity and the ability to handle and deal with data better and faster. And that in turn has allowed these four, what I see as four themes in the data space, the past, the present, the predictive, the action, as we collect, collate, curate, and crunch data. I just want to mention here that the crunch story is not just about working within a single data set, but also mining and interpreting data across a curated group of data sets, much like an art exhibition is curated, and you get a bit bigger story. The other thing to note here is that this is not just a story about people's expertise, but also that of computers themselves and advanced programming. And because, yes, we do have computers and systems that can learn without being explicitly programmed or constrained by what people would think, notice, or predict. And one of my favourite stories here that I heard a couple of years ago of curated data analysis and prediction relates to the horse meat scandal of Europe some years ago. And it's been shown since that this scandal could have been predicted without a single lab test being done, if at the time we'd looked across data sets for meat demand and economic data and supply chain information. Unfortunately, the fipronil in eggs issue wasn't one that could be predicted because it was the result of an inadvertent error in the supply chain. An example of the advances in science and tech has been the proliferation of devices and sensors for diverse applications, and certainly from what I see, their development continues at pace. There's just a plethora of these things for remote temperature, movement, geolocation, water level, water quality, milk fat levels, stirring rates, on-farm milk testing, in animal stomach boluses, animal collars, pest detection, advanced imaging, camera systems, handheld testing devices, and on it goes. And a lot of them are in the agri-food space. These devices are also increasingly connected to decision support software to not just be a data source, but to actually provide us with information and insight and options. I'm going to start today with the story by looking at an animal on a farm wearing a testing device. In this case, in the form of an ear tag. Doesn't do chemical or microbiological organism testing, maybe I should say yet. But it does provide a number of data parameters, and it does demonstrate developments in the field of in-field sensors generally. In this particular case, the tag provides farmer with temperature and movement data, as well as geolocation, and it's all done through a low Earth orbit satellite, and it contains an RFID and talks to other RFID-enabled devices as well. So what we're getting from something like this is primary test data, in this case, for example, temperature and whether the animal is moving or not. And one of the things that we need to think about when we think about data is that each data point has a positive aspect, but it also has a negative aspect. You know, the animal is here and it's not there. So you've got two data points. We're also getting data from an accelerometer that's on the tag, which we can mine for insights, you know, whether it's for animal behavior or wealth or health or welfare or something else of interest to us. And it's by taking an end-to-end supply chain view that then allows us to more easily ask about what are the implications upstream and downstream from data from the suppliers, and before the farm gate, all the way up through to the consumer. And then perhaps wrapped around this is another data set of information we're also gathering about compliance. And what we then have is the digital and informatics central database where we do our data analysis, because it's a repository of data silos and accesses data from external data sets as well. So what we've actually got then is this hyperconvergence, the talking of science and tech devices with data through this informatics central place. And this connectivity then provides us with feedback loops and the ability to apply artificial intelligence and develop digital twins for your business. And by that, I mean converting a physical asset to a digital asset, converting a physical process to a digital process, And then modeling your business end to end, so you can do what if experiments and test and predict and tweak your business in virtual world in real time, and you don't have to wait to see what the financial consequences. Reality, absolutely. The building blocks of this sort of thing are already in place and are available through and in use by organisations and some of the sort of startups, for example, the smart irrigation people, right through to the likes of Amazon, their AWS system, and Microsoft. Now, in truth, the AirTag that I talked about, started off this off with, has actually got on-tag data analysis capabilities as well, because more and more sensors and devices are being built with algorithms in their programming to create these smart devices. And so by taking advantage of those sorts of things and applying your artificial intelligence, we're able to create what I'm calling intelligent supply and value chains through an internet of smart things. And the value proposition for that really is about real-time risk and opportunity management, as I see it, rather than a pure cyber-physical efficiency value proposition. So, to the next part, having set that scene, let's ask now about the lab of the future and what will it be. What I'm going to do here is look at some advances for testing and lab processes, and then I'll also join some dots as I see them anyway. One of the ways that I've been looking at the questions is through this innovation model: breakthrough, game-changing, disruptive, incremental. And the lens of the 4 themes that I mentioned earlier. I'm just going to work through a few of these advances in science and tech and digital capabilities more from a lab context. So from incremental innovation, I mean, that will be common to all of us, looking at better processes, finding a better way to do things. And in the lab, new ways to prepare samples or run tests, a better instrument, which is always being offered to us, better analytical power maybe, better detection limits, better precision, reproducibility, better database support, maybe even better ergonomics. If not also a new application for the lab of existing tech, something that sits in the lab's focus. What about something a little different? NMR instruments, moving from specialist and research facility labs into routine use in the commercial space, if not also in industry. Spectroscopic technologies, secondary methods, using parts of the electromagnetic spectrum like infrared or near infrared, Raman technologies and the like, increasingly common and being applied. Digital tech, apps for sample submissions and access into LIMS systems, RFIDs and NFCs instead of printed labels and barcodes. Already here and well established. But before moving on a little bit further, there's a couple of new technologies with their potential for the food lab this afternoon. Both are mass spec techniques that I'd like to draw attention to. Neither is new, they've been around for some time. It's just that they're finding wider applications. And they're a bit like the time of flight systems where you have the opportunity to do targeted analysis as well as analysis, untargeted analysis. You don't have to know what you're looking for. And importantly, both of them are ambient mass spec systems, chemical and biochemical analysis. And the sample is presented directly to the instrument without extraction and purification. So great saving. The first of these is DART, Direct Analysis Real-Time Technology, which is now advanced to the point of multiple sample applications instead of just one sample at a time, and partial automation because of the growing demand and application for this instrument type. And the second is the iKnife, technology originally from the medical world, where it's used to differentiate between cancerous and non-cancerous cells real time in the theatre during surgery. But it's being used, for example, for meat speciation and authenticity. Apparently it works well on samples containing water. I imagine that. It's usually anathema to many lab systems. And we have one here in New Zealand in ag research at the moment, but not in a commercial lab. Another one I just want to quickly highlight too is this nanostring technology, in case I'm accused of a chemistry bias. And perhaps this is the case of hello nanostring, goodbye PCR, and a different approach to metagenomics. Remains to be seen. The tech about this is, and I'm going to read this, direct hybridization-based digital detection and counting technologies for multiplex profiling of pathogen and host-specific responses simultaneously. Yes. And admittedly, this is from the health sector. But when I do my horizon scanning, what I tend to find that what starts in the health sector fairly quickly moves into the animal sector. And when it's in the animal sector, it quickly moves into the food sector. So perhaps something a little more game-changing or disruptive for our current laboratories. And I mentioned earlier the advances in computing and the ability to handle and model data more faster, which has enabled this whole suite of omics testing, still again mostly found in specialist and R&D labs, but offering invaluable data and insights on genome functioning and structure and metabolism through this growing discipline of data sciences being called bioinformatics. And I know this type of approach is being used across mass spec data in some labs. Advancing data sciences in this bioinformatics piece and advancing computer programming and capabilities, what we commonly call artificial intelligence, AI. And I know that this is, for example, already in use in labs to improve existing methods and to identify new methods for a new test, better data modeling. And I note that SGS is now offering contaminant risk monitoring, leveraging AI, data and dashboards. And I read this morning of an organisation in the UK that says it's doing reliable ecotox assessments through AI systems without the need for any testing on animals or biological systems or in the labs. One of the other areas that I've been paying attention to was wearable technologies, wearable computers, voice and gesture control computers, extended reality applications. And these things are growing in diverse, applications are growing in diverse fields now. And I can see applications in a lab, but I don't see anyone doing that as yet. And then this example came up just very recently for me. And it's a picture of where extended reality is being used together with a handheld device and mapping software to assist in pathogen monitoring programs within processing and manufacturing plants. I want to touch briefly too on automation. Off-the-shelf automation options and software are pretty common, whether it's for part of a process or whether it's for a whole test. And we have bespoke robotics as well, a little more innovative, a little less common, but again, nothing new. The image there of Miss Eugene in Singapore, I'm not quite sure why we have to make robots look and work like people, and then why we have to put them in a separate room and keep them away from other people in case people get hurt. Was perhaps the better way forward is this robotics situation. A little more disruptive and game-changing perhaps, where a human and a robot actually share control, but I've yet to hear of this in a commercial lab setting. And the fully automated lab all seems to be a thing of science fiction for at least the food space. The closest I've seen is the medical labs, where they have a lot more automation of end-to-end process, able to do multiple tests on a single instrument. And the challenge for food labs, of course, is the diversity of sample types and test types that they have to do in food safety, quality and composition. Mobility, mobile labs, been around for years, nothing new here from what I've seen. It's all incremental innovation, taking what we have, putting it on a mobile platform. But how often have you heard the cry from more sophisticated labs using mass spec? Mass specs will always be in a lab of some sort. There's no other choice. Well, how about this? Here you go. This is a portable mass spectrometer being used for pesticide analysis in a cornfield. And yes, you can buy one now. They are available. There you go, 90 to 120K, depending on the options. Our in-lab equipment is getting smaller and more compact. And as I see that happening, I think, well, that must also portend that tech is going to be enabled to move out of the lab and will continue to do so as it becomes increasingly sensitive, capable and multiplexed. And so, yes, portability, miniaturization continue to be a focus of capability development, physicochemical, chemical, biochemical, microbiological measurements, including whole genome sequencing there in the middle, the MinION, taking that out into the field. And some of it might be set up permanently in the field, or you take it with you at the time, as in that middle suite of images there. Some of it will be handheld. Some of it may, in fact, be machine held, like it as in a drone there. And data might be crunched on the device itself, or it's crunched on a computer attached to the device, or the information is sent to the cloud and returned to a device like a cell phone. So here's a set of on-farm capabilities for the dairy farmers: real-time cow-side milk testing for composition, safety, quality, some disease parameters, some in use, some in development. But imagine what you could do and what you wouldn't need to do up or down a supply chain if you were able to integrate this data and feed it into an Internet of Things, an integrating data model, as I started this talk off with. There is an increasing plethora of devices and a great deal of R&D going on around the world, and even here in New Zealand, in doing this type of work. Some of it requiring sample preparation, and if it does, then through microfluidic or nanofluidic systems, and using new and different ways to trap analytes, to detect them, to measure them, including using the electromagnetic spectrum a lot more, the absorption, emission, sort of photonics. And I haven't got a picture of the device here, but there is the ability to, for example, to do E. coli in water using spectrophotometric methods. And there's a device available in Germany that does total viable counts in 3 seconds on surfaces, including food surfaces. And I also want to touch on, back to the non-sample preparation piece, by looking at a bit of image analysis and various machine learning approaches. So also finding broad application in the production systems and in the food industry now. I don't know if any of you have heard of Agro Ninja. They are using photographs to calculate the weights of animals on farms to 95% accuracy. It's pretty smart. They haven't quite moved to all New Zealand's herd type, animal types yet. BrightScan, using image analysis to determine authenticity and fraud in herbs and spices and some food products. In fact, in the herb and spice area, they've now got 100 different products that they can test just by doing image analysis. And of course, if you can see something as a person, then why can't the camera see that? And why can't it be more effective? Because a computer is attached to it and it has the memory, a better memory than humans have, and can recognize relevant points which we couldn't. And of course, all of this leads to applications moving past white light into multi and hyperspectral imaging and its uses in food composition, quality and safety, something which is being done here in New Zealand, not just on farm and in pack houses, but also in a laboratory space for meat speciation and meat quality through ag research. But I need to start drawing this to a close. And so I think one of the takeouts that I've got is that words like disruptive and game-changing don't carry quite the same weight for me that they used to, as I become aware of proof of concepts that move to proofs of application and that moves to application. The breakthrough innovation piece, it's rather harder, especially when you think about the laser technology on which so many of our communication systems are built these days. Didn't come into reality until somebody could build a clean room that was clean enough to make the lasers. So how do you scan patents, for example, and understand what the applications might be? And there's a great deal of interesting research being done around the world. I would have liked to talk about some of it this morning, but I'm bound by confidentiality agreements to not say these, unfortunately. So please keep watching. But just to step back then, what really excites me most about these advances in the science and tech and the digital worlds is the new business operating models, opportunities that they open up, and the challenges for laboratories, which to my mind, these things are interesting and important. Some of my lab colleagues, they constantly challenge me with, all you're trying to do, take tests out of the labs and take away my jobs. And I report, no, all I'm trying to do is challenge you to think about what you do, how you do it, why you do it, and what you could do for your customers, given a changed and changing science, tech, and digital world. And if you stepped past the lab and into the supply chain. The EU's FASMA food and smartphone projects are doing this sort of thing, working on devices, in this case for real-time pesticide, allergen, mycotoxin, food spoilage organisms, marine toxins, predicting shelf life by hazard detection and early signs of spoilage for industry and for consumers. They aren't the only ones pulling together the 4 science and tech themes and the data themes. You've got Telspec and our own Hamilton-based Sigito, for example, with their NIR lab in the hand tools. Both using the cloud for test and reference data storage, advanced data sciences and algorithms for data interpretation and prediction, subscription models for test results, data access and insights. And really, it doesn't matter where the hand is, whether it's in the lab, in the field, in the production or the manufacturing site, whether it's in New Zealand or whether it's somewhere else around the globe. Imagine that. So generally, what I find is that our lab guys are good at focusing on the test, but they're not so good on the big picture. The needs and opportunities that will arise from having these in-field, in-situ devices, sensors, testing, their repair, their calibration, and they're actually not self-repairing or self-calibrating as some are, replacing them when they fail, the need for reference materials, the need for data sciences, programmers, the skill set needs of a bigger picture and a longer supply chain view. After all, why would you have a bricks and mortar infrastructure and staff with the wrong training for the future, adding costs to tests that you don't need to add to, and when you can do fit for purpose testing in situ? The leap of faith, as I see it, is that if we better understand the status and risk associated with any parameter we want to test, we might want to have data for, and obtain this data and information from inputs at all points in the supply chain, increasingly real time, and we can better mitigate and manage this risk, and we wouldn't require as much in-process and input endpoint testing. So is this the lab of the future? Yes, it's meant to be a black screen, lights on, lights off, nobody home. Or will it be a little bit more like this, Informatics Central, a data science, intelligence and comm center that is connected, receives, curates, collates, crunches data, manages risk, helps manage and maximize opportunity. Of course, it's never as easy as it ought to be, and so maybe it looks a little bit more like this. Top left there, the new lab, a little sample reception area, because really you're not going to get so many samples into the lab as you used to. Top right, an area of lab-only devices, because you actually can't take these things out of the field. Bottom left, the new laboratory bench for data scientists. And bottom right, data scientists hard at work. And of course, out the back, we've got our area for storage of devices and sensors and calibration and reference materials, repair facilities, and the associated staff. So my takeouts from the horizon scanning and my wayward thinking, laboratories were once the church of science and tech. They aren't anymore, but they could be again if we recognise that it's not about the test really, and nor is it really about the data. It's about developing an integrated platform and knowledge on the supply chain and thinking about a different definition of what we mean by a lab. I certainly see that bricks and mortar labs will be fewer, and those remaining will be high-end and integrating and reporting on supply chain and other relevant data sets. This course is going to have significant impact on the type of people that we employ in labs. Science fiction, well, you have to think that the most influential product prototypes of the early 21st century were dreamed up in the pages of monthly pulp fiction only a decade ago. And the gap between science fiction and science fact is shrinking at an ever-increasing rate. And so it adds to the truth of what L. Ron Hubbard said. The person who says something can't be done is usually interrupted by somebody doing it. But the challenge, as I see it, is that the gulf between those embracing science, tech, and the digital developments in the lab space and those who don't and are falling behind is growing and getting so faster. And that's just going to make catching up so much more difficult the longer you leave it. We must avoid the time when it's going to be too late and the event horizon has overtaken us. So with that, thank you for your ears. And a statement that I must say is that what you've heard is my personal view. There's absolutely nothing about what assure quality is or isn't doing. Back to you, Vivian.
Thank you very much, Harry. That's great. So Tim, if you'd like to just share your slides while we set up, there is a question for you, Harry, from Steve. He asks, thanks for your presentation, and where does blockchain and analytical info fit in your view? A quick answer on that.
The blockchain is just a system for shifting data around, and so it's one of the tools of an integrated data set or integrated supply chain view of how to handle data.
Yeah, okay, that's great. Thank you. Okay, we'll hand over to Tim and then we can take further questions as well if you just want to send them to me. So Tim and Matt, over to you.
Yeah, thanks Vivian, and good morning everyone, and thank you Harry for a great presentation. That was awesome. So Matt and I are briefly going to talk this morning about a New Zealand Food Safety Science and Research Centre project on commercially available rapid test kits for bacterial pathogens and chemical contaminants, and how this technology can be better adopted by New Zealand food producers and processors. So an output of this project is a website that we've developed to help industry identify and select test kits that would be appropriate to their situation. And we've called it Food Safe Test Kits for Industry. And as a proof of concept, we've developed a website or trialled it on the priority pathogen Listeria monocytogenes. And Matt's going to be speaking a little bit about the website in a few minutes. But as a bit of a background, we're fully aware that rapid test kits are continually being developed and promoted for pathogenic microbes and other contaminants, chemical contaminants, natural toxins, etc. And that these tests have some advantages over existing testing approaches. We're aware that the food industry is regularly bombarded with promotional information about these testing kits, and that it's hard for industry to collate all of these options and to objectively filter them based on their pros and cons. So there's this need for a one-stop shop for targets that are important to the New Zealand food sector. And the centre has identified that, we've heard that from industry, and a project has been funded that I'm just talking about now. The first phase of that project has been 100% government funded, and any future phases of this project will require industry contributions. The aims of the project were to establish a database and assessment framework for commercially available rapid test kits for microbial and chemical hazards in the food chain. And then secondly, to develop this web-based platform to display the information for industry to access. Our first task really was to put together a working group of key technical people across industry. And we formed that group with representation across multiple sectors, dairy, horticulture, seafood, red meat, and we had representation from our competent authority there as well, MPI. We started with a survey to the working group to best understand the needs of industry and attitudes around rapid test kits, and we asked 6 key questions, and I'll summarise the key findings of those just in the next couple of slides. The first question was around what are the key organisms or contaminants that your business are wanting to focus on from a food safety perspective. And 3 bugs were identified as being of key interest across multiple sectors. So that's Listeria monocytogenes, Salmonella and E. coli. Other targets were identified by the dairy sector. And it's interesting to note that no chemical contaminants or natural toxins were specifically identified from this working group, but I'm sure there's interest elsewhere. Second question was around what are the reasons your business would want to use a rapid test kit? And the primary reason was around the timeliness of results, but there were other reasons there as well, which I've listed: improving quality of product, assessing effectiveness of cleaning regimes, aid troubleshooting, and reducing monitoring costs. Question 3, does your business use a rapid test kits? And if not, why not? Most industries were not using rapid test kits, but all were interested in exploring their further use. And the main reason for not using them was that there wasn't a systematic approach on how best to identify and assess the tools that are available commercially, and that they rely on information provided by suppliers on their performance. Fourth question was, what are the minimum requirements of a rapid test kit must have to be considered within your business? And the primary reason that they need to be quick and easy to use, and that they're validated to an acceptable level, with MPI being a key assessor of that. Minimum requirements of what's needed. Things like sensitivity and selectivity are key parameters which are regarded as highly desirable with these test kits. So the last questions were around identifying what the barriers are for industry around adopting rapid testing technologies, and multiple barriers were identified. I'm not going to go through them all, but you can see them there. There were plenty. The final question was around what information would be of greatest use to businesses to help overcome these barriers. And the 2 key bits of information that came out were that there's an independent assessment of the performance of the kits would be really useful to inform decision making by industry around the appropriateness of these tools, and that it'd be really useful to have a centralised repository of information that industry could draw on around the different kits that are available and their performance. So the next steps in the project were to incorporate the key survey insights into an assessment framework so that vendors could be approached for clear and consistent information about the test kits that they supply. And that would allow us to objectively assess each test kit based on the information provided. And then the third step was around identifying a way that we could effectively share this information with industry. And that's where I'll hand over to Matt to talk about the website that we've developed. Thanks,
Hello,
Matt.
everyone. Thanks, Tim. So we had to put the database together around Listeria products, and it was quite hard to look at the websites and the information out there. So we went directly to the vendors because they had the information, and they had some skin in the game. If they wanted their kits involved, they want to put the good information in there. So these are the 4 different vendors we have. It's probably not everyone out there, but we were hoping industry and other people can provide gaps in the data set. And we also approached a company here based in Nelson, a web development company called Upshift, who they were the ones that behind the web development and helped us with that. So before I get over to the web site and database that we've developed through these different sites, I wanted to have just a quick chat about that it's out there at the moment. We've launched this site, and it's been launched from the research website, and we're looking for feedback right now. It's not perfect, it's a beta version of the site, and we know that we want to change some things, but instead of changing it piecemeally, we want to get as much comment back from people before we start playing around under the hood. So if you do have comments, and we do implore you to go out and have a look at this website, post this webinar, please email them through to Tim Harwood. His email's there in this slide. And also, it's not the end here. There's a whole lot more. There's a whole lot of next steps that we want to go on there. So we do want to improve the functionality, improvement of the website, but we need some feedback. We want to keep this updated because this is a pretty rapidly moving space. There's new kits coming online and one's dropping off, and we want to keep it up to date. So how often and how do we go about updating the database? We want to engage with the industry group to make sure that we capture all the Listeria kits out there. We only went to 4 vendors. We feel that represents most of the industry, but there'll be things that slip through the gaps, especially if companies or industry are getting kits from international sources. And then we want to expand the database to other pathogens, and Salmonella and E. coli were 2 that were highlighted by industry that were interested, but also contaminants. But probably the other thing that we need to work with the MPI is develop an action response to if you do get a presumptive positive test, what happens next? And we need to work and try and put some information around that. So I'm going to play around with my computer here so I can just show you the slides, and I'm hoping that this will quickly flip over to here. So if by way of nod, Tim, can you see? Yep, okay, so this is the database behind it. This is an Airtable, which is a spreadsheet database. And I just wanted to show you this quickly, just because the flexibility of that. I can update information along here and then update it in real time. So we can add new kits, add information without going out to the web designers and spending money and trying to get a third party. And this is a pretty quick and easy method that we have that we can quickly add and subtract data as it comes online. And that can be done quite quickly. And without further ado, here is the website. So this is the food safe test kit. At the moment, we only have 2 pathogens, or 1 pathogen, Listeria mono and Listeria species. The 4 different distributors that we've done before, uses that you could click on, and there's a whole ribbon here of things that you can choose, whether you want it for laboratory use or in-house. If you're looking for environmental or food, there's your test material and some ease of use. And these have little definitions, so you can easily say, hey, I want to look for something that requires a PC2 lab. I can do right up to the harder ease of use or the level of training. We try to keep the functionality of this website easy to use and accessible for industry. So you could sit there and choose a couple of things. You want a monocytes, you want it in-house, you want it for environmental conditions, and the choices change with you. And then you can also compare up to three different ones at a time, and you get a whole lot of information where you can look side by side on each kit of those three different kits. But if we look at just one kit, you can see the website, then that will link through to a website on the contact details of the company that's owning it, distributor's website, all this information about training and ease of use. We also leave an area here that we want to work with industry to make sure new industry people can understand and ask the right questions that make sure these kits are provided for them. And then there's a whole lot of information. Unfortunately, the vendors were very not inclined to include some information, important information like price, because their price is on a moving scale depending on customers and size of companies, etc. So somewhat important information is missing from this. And there's a bit of a chicken and egg thing. If we can make sure that this website is used by industry, maybe those vendors are more willing to provide that data. And they've all had a look at this website now and they see the benefit of it, but we actually sort of need the industry to start looking at it and talking to the vendors. And when they see the benefit of this website, we can actually put some more pressure on them to include things such as price and sensitivity and other things that they're unwilling to share with at the moment. So feel free to have a look at that website. You can get it through the Centre's website. In the news section, there's a link there. Or I think if you do Google's food safe test for New Zealand industry, you'll get there quite quickly. And we're really keen to hear feedback. So please keep those questions and information coming through to Tim.
Great, thank you. Thank you, Tim and Matt. I do have a couple of questions that have come up, so please send more if you have some questions of Tim and Matt. But one question, I think this is for Harry, was using non-culture methods usually provides false positives when testing for Campi. Only 80% of those samples have found Campi are confirmed if the samples are cultured. Can we rely on on data that uses non-cultured detection methods? I don't know who wants to answer that. Harry? Put yourself not on mute, Harry.
Way beyond my pay scale, that type of technical information.
Maybe Tim, you can answer that, or Graham.
Yeah. Look, I think they are talking specifically about these rapid test kits that are being promoted, and that type of question is exactly the type of question that's needed to drive the interrogation of these kits and how they perform, and we need that type of information to determine whether or not they're appropriate to be used within food production and processing facilities. I can't answer it directly, but we need that type of information for these kits to be available to assess whether or not they'd be appropriate for use or not.
Okay, I've got a very long question here from Phil. This is to Harry. So as testing becomes cheaper and easier, do you see a time where consumers will have the technologies at home to enable them to check apples for pesticides or meat for the presence of antibiotics or E. coli? Presumably such devices will be connected to the cloud so that results, presumably bad results, could be quickly shared to consumers and then eventually back to the producers. Is this a brave new world which will ensure accountability and safety, or will it potentially lead to chaos? His point is that it's one thing to get excited about data collection, but we know that consumers, media, and scientists struggle or are unwilling to understand the risk. Therefore, do we run the risk of technology backing us into a corner, checking if our food is safe or not?
Yeah, exactly. And certainly when you look at what the FASMA Food Project, EU Smartphone Project, entities like SCIO, based in Israel have been looking at. They did start from a citizen science point of view, and you can just imagine some of the outcomes of that. But what I find interesting now is that SIO, for example, has pivoted away from thinking consumers will be the end users of these devices. Yes, some may have access to them. They may be devices in their own right, or connected to a smartphone like SIO was trying to do with Huawei. But SIO has pivoted away from focusing on consumers to actually building the systems and the data systems more for industry and processing and manufacturing and on-farm use than for consumer use.
Oh, that's great. Thank you, Harry. Any other questions from, we're sort of running out of time. I do like to try and get everyone away in 50 minutes or 55 minutes. So I really appreciate your talks on both Harry, Tim and Matt. I think that was really, really interesting what you talked about, Harry, the big picture perspective. I mean, food testing and testing in lab has changed a lot since my early days of testing in the dairy lab in the 80s. And, you know, it's great to sort of see, you know, there's some opportunities for New Zealand. I'm interested in some of the companies you mentioned, one in Hamilton. And I think that we have to look at sort of, given what's happened with COVID, there's some real opportunities in this space for New Zealand innovators, I think. And Tim and Matt, I think that's great work you've done with that website. It looks really interesting, and I hope that the industry will give you feedback. We have quite a few people from industry on the call, so that's really good. And just want to tell you about the next seminar, which is going to be held on the 26th of June, and it's Jan Powell from ESR who's going to present us, her work on the microbial challenge studies to validate food safety controls in food production, and the ups and downs of setting up a New Zealand reference collection. So I think that you'll find that interesting, with specific to New Zealand, and look forward to seeing you all again on the 26th of June at this time, 10 a.m. So thank you very much, everyone, for calling in, and appreciate again the three speakers.
Thank you. Bye-bye.
Okay, ka kite anō.
Thanks, Harry. Thanks, Vivian.
Thanks. Bye.
Thank you.